In today's video, we'll take a rather unconventional approach to understanding electromagnetism. Instead of assuming from the start that electromagnetic waves are sinusoidal oscillations, we will derive the actual expression for the oscillating electric field in space due to an accelerating charge. We'll also visualize the field we derive, making the process more intuitive. To build our foundation, let's start with Coulomb's law, one of the simplest equations in electrostatics. It describes a radially outward electric field around a charge. However, there's a fundamental limitation. Coulomb's law applies only to stationary charges. What happens if the charge is moving or accelerating? Coulomb's law does not account for this scenario. This brings us to the radiation field, which acts as a correction term to Coulomb's law, incorporating the effects of charge acceleration. Unlike Coulomb's field, which falls off as 1 by r squared, the radiation field is inversely proportional to r. This means that at large distances, the radiation field dominates over Coulomb's field. Thus, in most cases, we can ignore Coulomb's law and focus solely on the radiation term when analyzing electromagnetic waves. Another key difference: the acceleration used in this term is not the real-time acceleration of the charge. Instead, it is the retarded acceleration, meaning the value from an earlier time proportional to the distance of the point from the charge. This delay occurs because information, including changes in the electric field, cannot travel faster than light. In essence, electromagnetic fields behave like information carriers that propagate at the speed of light. To understand the direction of the radiation field, let's plot the acceleration vector of the charge and the radius vector to the observation point. From this, we extract the perpendicular component of acceleration relative to the radial direction. According to our derivation, the electric field vector is aligned, or anti-aligned, with this perpendicular component. Now, let's visualize the bigger picture by plotting the electric field vectors around the charge as it oscillates along the z-axis. These field vectors are dynamically updated based on the real-time acceleration of the charge. At first glance, you'll notice something peculiar. The electric field vectors seem to align with the z-axis. Why is that? At large distances, the perpendicular acceleration component becomes nearly identical to the acceleration itself. We'll explore this further when deriving the vector expression for the field. Of course, we cannot ignore the magnetic field. As we know, electromagnetic waves consist of two interdependent components: the electric field and the magnetic field, which oscillates perpendicular to the electric field. For every electric field vector we plotted earlier, there is a corresponding magnetic field vector, which lies in the xy plane rather than along the z-axis. Notice how the pattern resembles the circular magnetic fields around a current-carrying wire, except here, the directions continuously change as the wave propagates. This is consistent with our previous discussion on electromagnetic waves. Now, let's mathematically derive the expression for the electric field. For simplicity, we assume the charge follows a basic simple harmonic motion. We also make two key assumptions. First, the observation point is far away from the charge. This allows us to approximate the perpendicular component of acceleration as nearly equal to the total acceleration. Second, the charge's oscillation amplitude is very small. This lets us approximate the radial direction as nearly constant. The derivation itself is straightforward. Compute the cross products as required by the radiation field formula, substitute the retarded time correction, and arrive at the final expression, which closely matches the familiar textbook formula. However, one key distinction: the amplitude of the radiation field is not constant throughout space. Instead, it decays as inversely proportional to x, just like the radiation term itself. In practical applications, we don't usually deal with a single accelerating charge. Instead, electromagnetic waves are generated by a continuous distribution of accelerating charges, such as in antennas. Through superposition, these sources collectively produce a uniform plane wave with a nearly constant amplitude. This deeper discussion is beyond the scope of today's video, but it's a fascinating topic for another time. Finally, let's plot both the electric and magnetic fields together, constrained to a single axis. As expected, we get sinusoidal electric and magnetic waves, oscillating perpendicular to each other, the classic structure of an electromagnetic wave. And with that, we have successfully derived and visualized the fundamental nature of electromagnetic radiation. We started from Coulomb's law, identified its limitations, and introduced the radiation field correction. From there, we derived the electric field of an accelerating charge, visualized how the radiation field dominates at large distances, examined the magnetic field component, and finally plotted the complete electromagnetic wave. In future videos, we might explore the superposition of multiple oscillating charges and how antennas generate real-world EM waves. This concludes our discussion on electromagnetic wave generation.